So, hello and welcome to the next part of this tutorial. Today I would like to show you how to pick something in the three-dimensional world using the mouse. So I'm having here my plane terrain, and I would like to click now in this terrain and do something with it. For instance, changing the color or raising the height of these vertices where I'm clicking to. So how do we do that? It took me quite a while to figure it out, and most probably I didn't figure out the most effective way, but I'm still, it's working for me, so I'm gonna share it with you guys. So the first thing to know is there are quite a few steps between the two-dimensional screen space, where the mouse is going around with the two coordinates, x and y, and the three-dimensional world space, where the whole terrain is actually located. There are some transformations and different matrices and direct 3D or DirectX, or also some other three-dimensional render engines are working quite similar way by transforming from different matrices until you end up on the 2D or in a 3D. But now we would like to do something on the two-dimensional screen which affects the three-dimensional world in there. And yeah, how to do that I would like to show you now. So let's start right away. So the first thing where we start, we would like to do something once we click with our left mouse button. So in the on mouse down event, I'm gonna add here, we already have here the middle mouse button set to look around and steer the camera, and now let's do something with the left mouse button. So case mouse buttons left, and let's do something here. So we're gonna call here a function which we're gonna write soon enough. So let's call it picking triangle. And in this function, I would like to give an argument of the current mouse location. So the x and y axis of the values of the mouse. And there's a way to save them easily into one argument. Point, let's call it mouse down location. This is a new point, and we're gonna use this one, the fourth overload, and we give it e.x and e.y. The mouse event argument e of our mouse event contains the x value of the mouse, of the tip of the mouse, and the y value, and we store them both in a new point which we call mouse down location, and this one I give into our function. So let's make this function. Let's simply write it. Let's just go down here, mouse up, mouse down, and let's call it private void. It doesn't have to give anything back, and it needs a point. And here in this function I simply call it the mouse location, because I might use it for something else later as well. So the mouse location contains both coordinates, and we have a method here which does something with it. So the first thing which we need is some points or some vectors. So to store vector information, we simply use the Direct 3D vector or the DirectX vector 3, type, and we're gonna need a near, a far, and a directional. So direction. So what we're gonna do with them? Yeah, in the near vector we're gonna save the mouse position, the tip of the mouse, but we're creating a position vector for DirectX, and I would like to make something like an arrow or a ray which goes from the tip of the mouse straight into the screen, so like 90 degrees straight into the screen. And out of these two vectors or point vectors, I gonna calculate a directional vector which shows me the direction of this ray, and yeah, then we kind of have an information of where we are shooting a ray straight into the screen, exactly on the position of the mouse on the screen. And yeah, let's just start right away. So the near vector as a new vector 3, and yeah, the x position of this vector 3 is the mouse location dot x, which we get from the argument, and the y is mouse location dot y. And we also need the set value. The set is into the screen, so that the higher than the value, the more we are into the screen, and the screen itself is exactly at 0. So that's our near vector. That's the start of the ray which we shoot into the screen, so to say. And now we need the far vector. So, and this is exactly on the same spot as the mouse, but much further into the screen, somewhere. So we are kind of making a line from the screen position into the screen, and so the x and the y stays the same, and we just need some value for the set. Let's give it 100. So the far point, so we have a near point and the far point. One is exactly at the screen and one is 100 inside the screen. And now we can't do much yet, because we're still this is still, the mouse location is still some in Screenspace, and we would need to bring this into the Worldspace, into the three-dimensional space to it's not, and we need to kind of put it in there. And yeah, therefore the vector 3, actually DirectX provides us with a pretty cool function. So we just type in near and dot, and there are some basic functions, and one is this one, unproject, and this one says projects a vector from screen space into object space. This is what we need. So unproject, and it has some arguments. So the first one is viewport. Yeah, we are using just a regular device viewport. We didn't create anything else, so just simply device. And now we need 3 matrices. Yeah, what these 3 are, I'm gonna explain in a moment. But how do we get them? Getting them is quite easy. What they do, it's a bit more complicated. So device dot transform dot that first we need the projection, then device dot transform dot view was the second one, yes, and then device dot transform dot world. It's the last one. So what did we do? We now moved the vector 3 with the 2 mouse coordinates and the 0 for the set to Worldspace. So we moved it into the devices Worldspace, and we gave all the information of the three matrices into this function. And what does it do? The Worldspace is really this three-dimensional world where all the coordinates are in 3D, 3 dimensions, and you can, everything is kind of absolute. It doesn't matter from where we look, the coordinates in this three-dimensional world is still the same, but if we move around, it still looks then different on the screen. So there is some transforming going on, and it goes from the world space where each model, if we have multiple models in there, has its own model space, and if we put it into this world, we just have to transform it into the world space, so they are all connected with each other. So there's a 3D world, the whole terrain is now in the 3D world, and this one is transformed into the view space, and the view space is nothing else but we kind of move now the camera. We kind of add now into this world this camera, and the camera we position exactly on the Z axis. So the whole world is now kind of so much spinned and turned around or transformed that the camera is looking at or onto the world from or along the Z axis. And then this whole thing is again transformed into the projection matrix. And this projection matrix is kind of the camera itself, how the camera is set, in which kind there are different ways to project than the whole view. So the view matrix is still three-dimensional, and so is the projection matrix, but the projection matrix is much more simplified towards how the whole view should be projected onto the screen later on. And then once the projection matrix, it's still kind of in 3D, but to get a two-dimensional picture, you simply can cut off the Z value of the object, and you have a very flat kind of picture, and this whole thing is then put onto the screen. And what we do now with this, we kind of bring now the screen vector, the vector on our screen, into our world space, or into our object space. And a lot of mathematics is being done in this function, and luckily we don't have to do anything of it. Explaining it much more in detail would make this tutorial way too long, and there are way better tutorials out there which explain this in a very, very detailed way. But yeah, I hope I got it kind of right, and I hope I kind of could explain it very well. But what they are doing, they are putting simply these 2 points, which are set by the mouse location, into the world space where the three-dimensional terrain is located. So we can then kind of find an intersection or yeah. So now we need a direction. We need array, and array is simply calculated some basic high school math. Direction is nothing else but subtracting one vector from another. So we're gonna subtract the near, the far from the near. So, and that's it. Now we have a directional vector, which points exactly from our mouse location into the screen. and already in object or Worldspace. So what can we do with it? I choose most probably the worst method ever. I simply go through all the triangles. I iterate through all the triangles of my terrain and check does the ray go through this triangle, and if yes, then do something. So as you can imagine, it is most probably a very very slow method, and let's do it therefore. So start a for loop equals 0, and the triangles are defined by the indices. So e smaller than, what was it, index count, that was it, and one triangle has 3 indices or 3 vertices, and so we always jump up by 3. So we go through all the triangles and check, does this ray or this arrow go through this triangle. And now we need another function, and it's in the geometry, in the direct 3D geometry class. So yeah, direct 3D geometry, and it has quite some cool functions like bounding box and so on. And what we need is this intersect tree. So the intersect tree computes the intersection of a ray and the triangle. That's all we need. And as we already can see here, we need an out argument. So let's do it. We need here an out argument hit location. So let's create this as well. What was it? It's an intersect information hit location. Intersect information hit location. So, and the rest is vector 0, 1, and 2. So the 3 vectors, 3 points of the triangle. And yeah, the first point of the triangle position is saved in a vertex. But one vertex is used by more than just one index, so one vertex can be used for more than just one triangle. And so we kind of need the vertex on the position, not I, but actually on the position of the indices of I. So the index of I, there where the index of I is, this vertex we need, and from that one we need a vector 3, which we get with the position. Here we are. So we go in, the triangles are built up with all the indices, so we go for index 0, 1, and 2 in the first 3 situations, and there we get the appropriate vertex position. And that's the first point. Now we kind of have to do this 3 times for all the 3 indices. So e plus 1 and I plus 2. So now we made our triangle, which should be controlled, and the next one is the ray position, and then the next one will be the ray direction. So ray position is where does the ray start, so where we're gonna shoot the arrow in, and it's exactly the same as our near vector here. It's exactly the mouse location on the screen, z-axis on the screen. And the direction we already calculated as well. It's this one. So we have a direction, and now one is missing, and that's the hit location. We're not really needing it now, but the hit location, oh, it's an out hit location. Here is where all the exact information of the hit is being stored. So in this whole thing gives it's a boolean. So it gives back true if this ray with this position and this direction hits this triangle. If they two kind of hit each other, then this function gives back true. So we're gonna put this simply into an if, and now we can do something with it. Now we can, for instance, change the color of the vertex, or yeah, let's do this first. So the verts on the position, it's actually exactly this one. So the vertex from here, dot color equals color dot red dot to ARGB. The to ARGB gives back an int value, and the vertex color needs to be an integer as well. So, and let's paint all three vertices of the triangle which the ray is hitting into red. So I plus 1 and I plus 2. So, and now let's check if it works. No, it cannot work yet because we need to update the vertex buffer. We need to put the new information actually into the vertex buffer, so the vertex buffer into our inside our painting loop is actually filled with this new information. So the vertex buffer, which we have vb dot set data, and we give it again all the vertices, which we have 0 and log flags. It's kind of the same as we already did previously, but we kind of have to call it here. So with the new vertex, or the modified vertices, are now stored inside the vertex buffer. So, and now let's see if it actually works. We have here now picking triangle, mouse location. Okay. So, and now I click this one. Yes, it works. Let's check this one. Yup. And click, and click, and click, and click, 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 click. Not that funny. So yeah, as we can see, I click into this triangle. It doesn't matter on what position, and it paints all the three vertices into red. So, bang. This one is red, 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 and of course it interferes a little bit onto the others, onto the lane, because this one is white, this one is red, so it goes over. But this triangle is pure red now, because all the three vertices are turned into red. So, and it does not matter on what location inside the triangle I click, it turns it totally. And it does also not matter from what angle I'm looking at it. It really computes now the very right position. Pang, 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 pang. Pretty cool, isn't it? So, yeah, let's add some thing more, I would also like to raise actually the height of it. Let's just go with so this vertex dot position. Onto this position we simply add now a vector, a new vector 3, and we just want to raise this vertex by something. And so we add a vector which first argument is the x value is 0, the y value we're gonna give it let's put it in a constant. Let's call it raise constant, and then we have a set value of 0. So what we do here now, of course we need to define this. Let's go totally up to the very top where all of our variables are. There do we have some floats. Yeah, here's, let's go to private float raise constant. Let's call it actually a constant. So raise constant equals by what 0.05 should be just right. So here we are. Raise constant, and let's do this now for the other two as well. Plus 1 plus 2. Now let's see if we can actually raise the triangle. Click, 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 click. Ha! So, and now I would like to paint actually around some terrain, and therefore we need to set the mouse move. So we are doing the same kind of as with once the middle mouse button is being pressed, but now just simply with the left mouse button. So we have a bool is left mouse down. At the moment it's not down, so it's false. We go totally down to the, where is the load height map? Mouse down, mouse up, and where is our mouse move? Mouse scroll. Where is the mouse move? Mouse scroll, mouse move, here it is. On mouse move, if middle mouse is down, nope. If left mouse is left mouse down, when this is true, then let's do simply the same as when the mouse button is actually being pressed. Point mouse down location, but this is, let's call it here mouse move location. So we will create a point mouse move location, and now we need to set the bool true. So mouse down, when the left mouse button is pressed, simply set this to true. So once we move around, we actually, it's being activated all the time over here. And mouse up, we kind of need to copy this. When the mouse button, the left mouse button is being released, false, and now a break. What's your problem? Yeah, of course. So that's it. So switch with picking triangle. So this is back, this left mouse down is back to force, and now we should be able to paint long. So let's go up here, and now let's paint our own terrain. Ooh. I think that's pretty cool. So yeah, there are some minor problems with this. The first thing is, once we stop moving the mouse, it stops racing the terrain, so we might be considering later to add some, I don't know, some timer or threads. And another thing is, once we actually raise some terrain a lot, so, and now we are looking through this triangle, and if I click on this triangle on the front, it actually touches all the triangles through the back, and so we not just raise this one in the very front, but also that one in the very back, as you can see. So yeah, this would require quite some more calculations, but I think so for the beginning it's quite cool. I wanted to do this since a while. This is by far my most difficult, most complex Hello World program I've ever created. Thank you very much for your attention. Have fun.